Good morning, students. Today we will discuss the concept of quadratic form, matrix of quadratic form, linear transformation, orthogonal transformation, method of reduction of quadratic form to canonical form. Right. So here, what is quadratic form? A homogeneous expression of the second degree in any number of variables is called quadratic form. We can write a quadratic form in 2 variables, 3 variables, and so on and so forth. 3x squared plus 5xy minus 2y squared is an example of a quadratic form, which is a homogeneous expression of second degree in 2 variables x and y. The definition for quadratic form is an expression of the form q equal to x transpose ax, which is equal to double summation aij xij I equal to 1 to n, j equal to 1 to n, where these aij's are constants. Is called quadratic form in n variables x1, x2, so on so forth, xn. If these aij's are real numbers, then this quadratic form is said to be real quadratic form. Every real quadratic form in n variables x1, x2, so on so forth, xn can be expressed in the form of x transpose x, where x equal to x1, h2, so on so forth, xn whole power transpose, whole transpose I am writing, which is a row matrix, and A is real symmetric matrix of order n. So every real quadratic form gives a real symmetric matrix of order n. The matrix which is real symmetric matrix here, right? So that is a symmetric matrix capital A, so which is called matrix of the quadratic form. If we find the determinant of that matrix capital A is 0, then we can say that given quadratic form is singular. Otherwise, that is said to be non-singular. Similarly, we can check this singularity by with the help of a rank of a matrix. So take the rank of A, which is if it is less than n, that is number of unknowns, then the quadratic form is singular. Otherwise, we can say that is non-singular. Now we'll check how to find the symmetric matrix corresponding to the quadratic form with the examples. First one, h1 square plus 6h1 h2 plus 5h2 square. So here given quadratic form can be expressed as rewriting the given expression quadratic form h1 into h1 plus 3h1 h2 plus again I am writing 3h2 h1, that is I am dividing the 6 into 2 parts plus 5h2 into h2. So that I am writing corresponding matrix of the given quadratic form. So 1 3 3 5, which is 2 by 2 matrix, that is of order 2. Similarly, you can see here ax square plus 2hxy plus by square. So here the given quadratic form is in the form of x transpose ax, where we need to calculate this a here, right? That is a h h b. You can see the diagonal elements, that is square terms which are involved in quadratic form. That is coefficient of x square is a, coefficient of y square is b. The remaining we are writing as the non-diagonal elements. So here you have 2h in the question. So 2h by 2, so which is equal to h you are writing, which is also a 2 by 2 matrix. Now you can see another problem which containing 3 variables x, y, z. The given quadratic form is x transpose ax. So where you can write a from the given expression. The diagonal elements are 1 2 3, and the remaining you can check here x, y, z coefficients. Accordingly, we can write capital A. The quadratic form X transpose AX is the given one. So here we are applying the linear transformation on this one, and the transformation is X equal to Py. That is, I am taking as equation number 2, which is a non-singular linear transformation, right, in which P is a non-singular matrix. As substituting this X equal to Py in this quadratic form X transpose AX, which again reduces to another quadratic form in which Y transpose By, B is P transpose AP, which is symmetric matrix. Therefore, this Y transpose By is also quadratic form, right? So they are converting a quadratic form into another quadratic form by applying a linear transformation, where this P is non-singular matrix. If this P is, right, orthogonal matrix, right, here you are taking again, I am taking A here. If A is an orthogonal matrix, then the transformation Y equal to AX is called orthogonal transformation. Rank of a quadratic form. To find the rank of the quadratic form, we need to find a rank of capital A. That is, if a rank R of capital A is called, here we can say rank of quadratic form. And next concept, canonical form or normal form of a quadratic form. Let X transpose AX be a quadratic form in n variables. So then there exists a linear transformation I am taking here, X equal to Py, and what is happening here, which transforms X transpose X into another quadratic form, right? You know already. So by applying linear transformation, one quadratic form converts into another quadratic form. But here this another quadratic form of the type, right, how it is, Y transpose dy, right? So that is nothing but lambda 1 y1 square plus lambda 2 y2 square plus so on and so forth, lambda n yn square, right? So if it is the given quadratic form in n variables, right, of homogeneous, right, converting into sum of square terms, only square terms, right? So this is called a canonical form of X transpose AX, right? So this is one of the important topic here, canonical form, right? Next, index of a real quadratic form. So that is nothing but the number of positive terms in canonical form, right? So this canonical form, right? So for the given quadratic form, you need to apply a linear transformation. Then you are going to get sum of square terms. In that sum of square terms, right, means that canonical form, you need to check for number of positive terms. Number of positive terms, and that is denoted by S here. Okay. And here next definition, signature. If R is the rank of the quadratic form and S is the number of positive terms in its normal form, then 2S minus R we are taking as signature of the quadratic form. Now we'll look into nature of quadratic form. That is the quadratic form H transpose AX in n variables is said to be is positive definite if R equal to n and S equal to n, or R if all the eigenvalues of capital A are positive, right? So when we are saying it is a positive definite, if all the eigenvalues of A are positive, right? So here we are finding eigenvalues of capital A and all the eigenvalues are positive, then we can say this is positive definite. Or you can check here the rank is which is equal to number of unknowns, and that is equal to index. Index is S, right? S equal to n. The number of variables is equal to index, and which is equal to the rank, then we can say that is positive definite. Next one is negative definite. So as you know, positive definite, you can write negative definite. So that is if R equal to n here and S equal to 0, or if all the eigenvalues of A are negative. Okay, so all the eigenvalues of A are what? Negative, means there is index is 0, right? So there is no positive terms, all are negative, right? So then we can say this is negative definite. Here you can observe rank is equal to number of unknowns and the index is 0. That is number of positive terms in canonical form is 0. This is one criteria. Otherwise, you can check to the eigenvalues. If you know the eigenvalues, check whether they are positive or negative. If they are all positive, then that is positive definite. If all are negative, then you can say that is negative. Similarly, you can write a positive semi-definite. Positive semi-definite. So if here, if R is less than n and S equal to R, okay, R is less than n and S equal to R, or R, if all the eigenvalues, all the eigenvalues of A greater than or equal to 0 and at least one eigenvalue is 0, right? So here rank is less than n, okay, number of unknowns, and S equal to R, right? Rank and number of positive terms are same here, but that is less than number of unknowns. In that case we can say positive semi-definite. Otherwise you can check here the all the eigenvalues, what are they? They are greater than or equal to 0. All the eigenvalues are greater than or equal to 0, means there are some eigenvalues, that is at least one eigenvalue which is 0 here, okay? At least one eigenvalue is 0, then we can say that is positive semi-definite. Next one is negative semi-definite, right? So here if R is less than n and S equal to 0, or if all the eigenvalues of A less than or equal to 0, all the eigenvalues of A less than or equal to 0 here, and at least one eigenvalue is at least one eigenvalue is 0, okay? So negative semi-definite, what we are taking here, so rank is less than n here, S is 0. S is 0 means index is 0. There are no positive terms, only negative terms, right? So in that case we can say negative definite, or otherwise if you go with eigenvalues, all the eigenvalues are what? Less than or equal to 0, means at least one of them is 0, right? So in that case we can say negative semi-definite. Next one is indefinite. So this is in all other cases. All other cases means the eigenvalues of A are some of them are positive and some of them are negative. Right? In that case, there is no positivity or negativity or positive semi-definite or negative semi-definite. Right? So some of them are positive and some of them are negative. In that case, you can check with indefinite. Some of them are positive, some of them are negative, and some of them are zero. Right? In that case, also this is comes into indefinite only. Okay, so this is about nature of quadratic form here. So here you have 5 points, right? Under this nature of quadratic forms. Right? So we are checking the nature of the quadratic form H transpose H, right? So by observing rank, number of unknowns, and index of the quadratic form. Otherwise, by checking the eigenvalues, whether they are positive or negative or containing zero. I hope this is clear for all of you. Now here you can see we have one law here. Sylvester's law of inertia. So what it says here, the signature of quadratic form is invariant. Invariant for all normal reductions. Okay, so this is one of the law here. The Sylvester's law, what he is saying, the signature is invariant here by all normal reductions, right? So we are applying the reductions here for the given quadratic form by using different techniques like diagonalization, orthogonalization, and Lagrange's reduction, right? So whatever method you are using to convert the quadratic form into canonical form, so that the signature remains same. Okay, so that is Sylvester's law. Now we'll look into the methods, right? So what I told you for normal reduction, so that we will look into now. So the methods of reduction of quadratic form. Or we can say this is sum of squares. Sum of squares form. So here what you have is so first one is diagonalization. Diagonalization. So that is reduction to canonical form, reduction to canonical form
ఎందుకు తెలుసా ఇంకా ఆఫ్
by
లో పెట్టిన సార్
reduction to canonical form reduction to canonical form by means of the using linear transformation or linear transformation. Linear transformation of quadratic form. And second one is orthogonalization, that is reduction to canonical form using orthogonal transformation. And you can see here the third one, Lagrange's reduction, right? So these are the three methods we have to reduce the quadratic form to canonical form, or we can say that is sum of squares form, right? So the quadratic form may contain square terms as well as product terms, but what we are doing here, we are reducing the quadratic form into canonical form, which contains only sum of square terms, in which we can check the index signature so that we can find the nature of the given quadratic form, right? So now you have three methods. So one is diagonalization, second one is orthogonalization, and third one is Lagrange's reduction, right? So here we are going to discuss only first one and second one, that is diagonalization and orthogonalization, right? So those two will explain with the help of problem, right? So that is reduce the quadratic form to canonical form by diagonalization is one method, and reduce the quadratic form to canonical form by orthogonalization, right? So first one is diagonalization. Diagonalization, right? So here in diagonalization, first we are going to consider the given matrix capital A, right? And we are going to consider the order of the matrix, right? And we are going to take I equal to in a in. If it is of n by n matrix, I am taking in a into in. Okay, now we will reduce this capital A to diagonal form by applying elementary row operations and column operations, right? So we are converting this matrix into what? Diagonal matrix, right? What operations we are using here? We are using elementary row and column operations, right? So the corresponding row operations will be applied on the prefactor here. Okay, row operations. Whenever you are applying row operations on this matrix, okay, capital A, you need to apply here. No need to apply here and here. Okay, you need to write whatever you have here in the next step. Also, you have to write the same here and here. Okay, only row operation you need to apply here. So if you are applying column operation here, okay, no change in this matrix. This matrix is as it is, this matrix is as it is. Here you apply the column operation. Okay, no change here, right? No change in this prefactor, only on post factor of A, right? So you have to continue this until you need to get what? This capital A into diagonal matrix. Okay, diagonal matrix. In the last, you are going to get which is equal to P transpose AP. P transpose AP. Okay, where P is what? Non-singular matrix. P is non-singular matrix, right? And here you can say the transformation is x equal to py, right? The transformation is x equal to py, right? And you can write the sum of square terms with the help of diagonal matrix, which is on the left hand side. Okay, the diagonal elements which are present in the left hand side, with the help of that you can write the sum of square terms. And here the canonical form, how you are going to write here is y transpose dy and saying, which is equal to, right, y1 y2 so on so forth yn into the matrix which is on the left hand side, and y1 y2 so on so forth yn. Okay, so this diagonal matrix which you have here, this diagonal matrix that you are going to write here, so which is equal to, you are going to get a sum of squares, sum of squares under the linear transformation x equal to py, under the linear transformation x equal to p into y. What is p here? P here you have, right? You got p here, right? So under the linear transformation x equal to py, right? So in this sum of squares, right, here you have sum of squares, right? So in this sum of squares you are going to check number of positive terms, right? So that gives you the index, and signature is what? 2s minus r, right? So this is the method diagonalization. And here next method what you have? Orthogonal reduction, right? So this is first method here, diagonalization, and next one is orthogonalization, which is also used for reduction of quadratic form to canonical form, right? That is second one. That is orthogonalization here. So that is I am writing a procedure to reduce quadratic form to canonical form by orthogonal transformation. It is orthogonalization, we can say, right? So here first you have to consider the coefficient matrix capital A, that is matrix of the quadratic form. Okay, so that is A is what? Matrix of quadratic form, because they are not going to give capital A here, right? So they are going to give you the quadratic form, and you have to find the matrix of quadratic form, and then you find out eigenvalues eigenvalues of capital A, and then you find the eigenvectors of capital A, right? And here find the eigenvectors of capital A corresponding to the eigenvalues such that the eigenvectors are mutually pairwise orthogonal. Okay, must be pairwise orthogonal, right? So here eigenvectors must be pairwise orthogonal, because we are what we are writing here, canonical form by orthogonal transformation, right? So these must be pairwise orthogonal. If they are not pairwise orthogonal, you have to make them pairwise orthogonal. You know the method how to convert into pairwise orthogonal, right? So we solve two problems on this method, right? If they are not pairwise orthogonal, and then you need to write the normalized eigenvectors. So that is E1, E2, E3. E1 is h1 by norm h1, E2 is h2 by norm h2, and you can write E3 as what? h3 by norm h3. Right? Now you can write this P, that is what a model matrix here, which is E1, E2, so on so forth, En, right? So depending on the vectors you got, so that you need to take here. Then this x equal to py, which gives the required orthogonal transformation, which reduces quadratic form to canonical form, right? So x equal to py here gives you the required orthogonal transformation here, which reduces the quadratic form to canonical form here. So since P is orthogonal, we have P inverse equal to what? P transpose, that you know, right? So that is here D matrix is what? P inverse AP equal to, you can write P transpose AP, P transpose AP, where D is diagonalized matrix, right? So now write the canonical form using lambda 1 y1 square plus lambda 2 y2 square plus 1 for lambda n yn square, right? So it is a diagonal matrix here, you know, it's a diagonal matrix with diagonal elements lambda 1, lambda 2, so on so forth, lambda n. So that the canonical form you can write here lambda 1 y1 square plus lambda 2 y2 square plus so on so forth lambda n yn square, right? So this is the required canonical form corresponding to the given quadratic form, right? So here you have a quadratic form here which containing square terms and product terms, and we are reducing that one into what? Only containing square terms. How we are reducing that? Second method, that is orthogonal transformation. You are going to check the vectors pairwise orthogonal, and you are writing the model matrix. You know the method how to convert that matrix, right? That is diagonalization. P inverse into A into P you have to take, you know, P inverse is P transpose, right? So that you can get the diagonal matrix with diagonal elements as what? Eigenvalues only. Okay, so so that you can write that canonical form, right? What is canonical form? Lambda 1 y1 square plus lambda 2 y2 square plus 1 to 4 lambda n yn square, right? So if you know the eigenvalues if you know the eigenvalues of the given matrix, then you can write what is the canonical form. Okay, what is the canonical form of the given quadratic form, right? I hope this is clear for all of you. So this is the second method here. To reduce the quadratic form to canonical form.